This is LeetCode number 480, sliding window median. The median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value, so the median is the mean of the two middle values. For example, if we have a list of 3 elements, the median is the middle element, which in this case is 3. And if we have a list with 4 elements, the median is the mean of the two middle values, which is 2 plus 3 divided by 2, which equals 2.5. You are given an integer array nums and an integer k. There is a sliding window of size k, which is moving from the very left of the array to the very right. You can only see the k numbers in the window each time the sliding window moves right by one position. Return the median array for each window in the original array. Answers within 10 to the negative 5 of the actual value will be accepted. The constraints for this problem are k is less than or equal to nums.length, so the size of our sliding window will always be less than or equal to our input array, and these two will be between 1 and 10 to the fifth. And nums I, so each individual element, will be between negative 2 to the 31 and 2 to the 31 minus 1. That means that each element is an integer. Next, let's go through an example. We are given an input nums with these values and a sliding window of size 3. First, we start at the first 3 values, which are 1, 3, negative 1, and we need to find the median of these 3 values. In order to do that, we would need to sort these 3 values and find the middle value and put that in our output array. Next, we move our sliding window over to the right by 1 element. So the next 3 values are 3, negative 1, negative 3, and we need to find the median of these 3 values, which we need to sort these 3 again and find the middle value. And we would repeat this until our sliding window reaches the very end of the input array. And again, we find the median and put that in our output array. The time complexity for this is, since we are sorting 3 values, or k values, k log k, and we are doing this n minus k plus 1 times, so O of n, and our overall time complexity is O of n k log k, and the space complexity is O of k because we're only keeping track of k values, or the number of values in our sliding window. Suppose instead of a sliding window, we have a window that only expands to the right. Our first window would look like this, our second window would look like this, our third window would look like this, and so on and so forth. And we need to find the median of each of these windows. Well, the median here would be 1, the median here would be 2.5, the median here would be 1. Well, this problem is identical to LeetCode number 295, find median from data stream. So in order to optimize our solution, we're going to use a solution similar to LeetCode number 295. We are going to use 2 heaps to maintain our sliding window in sorted order. Let's say our sliding window has these 4 elements. If we sort these 4 elements, we get negative 3, negative 1, 1, 3. We are going to represent the left half, or the smaller half, with a max heap, and we're going to represent the bigger half, or the right half, with a min heap. If our window consisted of 3 elements, then when we sort these 3 elements, we get negative 1, 1, and 3. And if our sliding window has an odd number of elements, we are going to let the left heap or the max heap have 1 extra element. If our sliding window has an even number of elements, then we can find the median of the sliding window by taking the mean or the average of the top of the max heap and the top of the min heap, which takes O of 1 time. And if our sliding window has an odd number of elements, then we can find the median of the sliding window by taking the top element of the max heap, which also takes O of 1 time. Using the same example here, our window is currently at 1, 3, negative 1, and that represented using 2 heaps looks like this. So to move our window over to the right by one element, we would need to remove this 1 and add a -3 to our window. Remove this 1 and add a -3 to our window. And so our final window using 2 heaps looks like this. So far, so good. We can still find our median in O of 1 time by taking the max element from our max heap. Next, so forget this example. What if we had a sliding window with the elements 1, 1, 1, 1? So that represented using 2 heaps would look like 1, 1, 1, 1. And say we need to move our sliding window over to the right by one element. So we need to remove this one and add a 2. How would we know which one to remove? What we need to do is, instead of just storing the values, we need to store the value and the index that the value is at. And so instead of this, we need something like this. That way, if we are going to remove this 1, then we know that it is this 1 here that we need to remove and not these other ones. Next, let's calculate the time and space complexity of our optimized solution. Finding a median is O of 1 time. Adding and removing elements from our sliding window is going to be O of... If you notice here, our sliding window consists of 2 heaps, and each heap is of size k over 2. And to add or remove an element from a heap of size k over 2 is log of k over 2, and that simplifies to O of log k. And how many elements or how many times do we need to add or remove elements? Well, an easy way to think about this is, let's say the input is 1 million elements and our sliding window is of size 1. So we need to add or remove basically n times, right? Let's say n is 1,000,000. So we need to do this n times approximately. That means our overall time complexity is O of n log k. And our space complexity is, if you see here, our window is always going to be of size k, so O of k is our space complexity. And you see our space complexity stayed the same, but our time sped up pretty significantly since we removed a k. To summarize, we're going to store our sliding window in sorted order using 2 heaps, and we're going to store the value and the index that the value is at on the heaps. So if we're storing this element here, we're going to store 2, 0 on the heap. And the left or the smaller half of the sliding window will go onto the max heap. And the max heap will always have an extra element when k, or the size of the sliding window, is odd. And the right or the larger half will be stored using a min heap. Suppose that our sliding window is currently from the first element to the 4th element. That means we will store, and this in sorted order is 1, 2, 3, 4. So to store on our heaps, it will look like 1 is at 1, 2 is at 0, 3 is at 3, and 4 is at 2. If our sliding window has the first 3 elements, then it will look like 1, 2, 4. 1 is at 1, 2 is at 0, and 4 is at 2. So you see, if the size of our sliding window, or k, is odd, then the max heap will always have 1 extra element. And to move the sliding window over to the right, we're going to follow this order. First, we're going to remove the old left. So let's say we're at here, and we need to move our sliding window to here. Then what we need to do is we need to remove the old left, which is 2, 0, and we need to add the new right, which is 3, 3. By the way, before we remove this element here, we need to find which heap it's located on. So if we use a priority queue, find takes O of k time, whereas if we use a tree set, then find takes O of log k time. So we are going to be using a tree set to represent our 2 heaps. Next, let's take a look at the code. First, we need a class to represent this tuple here. We're going to call this class tuple, and it's going to have 2 fields, value and index. And we're going to create a constructor. for the class. Next, since we're going to be putting this tuple on tree sets, we need some way for the tree sets to compare two tuples. For example, we need to tell the tree set that this tuple is less than this tuple here. And to do that, we need to implement the comparable interface. And the function we need to override is called compare. First, we need to compare the values of the two tuples. We're comparing this dot value with the other tuple's value. And if compare values does not equal 0, then we're going to return compare values. So what this means is if the values of the two tuples are different, so for example, let's say our tuples are 1, 2, and 2, 1, and we're comparing the values. If their values are different, then it won't return a 0. So that's why we are just going to return compare values. Next, what if their values are the same? So let's say we have two tuples, 1, 0, and 1, 1. Since their values are equal, so we need to handle the case where their values are equal, and to do that, we'll just compare their indexes. And we can simply say integer.compare this tuple's index with the other tuple's index. And it doesn't really matter which order this is. So for example, we can say that this tuple 1, 0 is less than this tuple 1, 1, or we can say that this tuple 1, 1 is less than this tuple 1, 0. It doesn't really matter which way. What matters is that we have a rule to say which one is smaller and which one is greater in the event that their two values are the same. And sorry, the function we need to override is called compare2, not compare. Next, we're going to initialize our two tree sets. So our tree set is going to be already a min heap. And in order to make a max heap, we just need to reverse the order. Next, we're going to implement our getMedian function. And what this function does is it returns the median from sliding window. So there are two cases. One is if the sliding window has an even number of elements, and the other is if sliding window has odd number of elements. So in the case where the sliding window has an even number of elements, in the case where the sliding window, which is this entire thing, has an even number of elements, you can see here that the number of elements in our max heap equals the number of elements in our min heap. And in the case where the sliding window has an odd number of elements, then max heap has more elements than the min heap. So how do we get the median if the sliding window has an even number of elements? What we would do is we take the top element from the max heap and the top element from the min heap. We take the values, actually, and then we find the mean, which is summing them and dividing by 2. So first, the sum is the top element of the max heap, and that gets us this tuple, and we need the value. So dot value plus min heap, the top value from the min heap. And we need a double. So let's cast these two values to double. And to get the mean, we divide the sum by 2. Next, if the sliding window has an odd number of elements, all we do is we take the top value from the max heap. So max heap dot first dot value. And remember that value is an integer, so we need to cast this to a double. Next, we're going to implement a function called balance heaps. And what this is going to do is it's going to balance our heaps according to the following rules. If the number of elements in our sliding window is even, so here, for example, then the number of elements in our max heap is going to equal the number of elements in our min heap. And if the number of elements in our sliding window is odd, then the max heap is going to have that one extra element. Let's write our rules here. What if by some freak accident our heaps become imbalanced and they look like this? So currently, min heap dot size is greater than, max heap dot size. And so what we need to do is remove the top element from the min heap and move it to the max heap, right? So first what we're going to do is we're going to create a reference to this element here. That is min heap dot first. And then we're going to add the element to the max heap. And then finally, we are going to remove this top element from the min heap. And we're putting it inside a while loop because we're going to keep doing this until our heaps are balanced. Or in other words, until this condition is satisfied. Min heap dot size is less than or equal to max heap dot size. And this is just the opposite of this. So is min heap dot size currently greater than max heap dot size? Yes. So we remove this 4. And now the two heaps are balanced. Next, let's consider another freak accident and our heaps become imbalanced like this. What do we do? Well, first, our max heap dot size is greater than min heap dot size. But if you notice here, our max heap dot size can be greater than min heap dot size. If the total number of elements in our sliding window is odd, max heap has that one extra element. It can't have 2 extra elements or 3 extra elements. So it will have at most 1 more. If the max heap has 2 or more elements than the min heap, then we need to balance the heaps. So what we do is first we create a reference to the top element in the max heap. So that's this element here. And then we add this element to the min heap. Next, we remove Next, we remove the top element from the max heap. And are our heaps balanced? Well, this has 5 elements and this has 3 elements. So no, they're not balanced yet. So we repeat this process. So make a reference to here, and then add 5 here, and then remove 5 from here. And now, are our heaps balanced? Yes, they are. In other words, we repeat this while loop until max heap.size is less than or equal to min heap.size plus 1. Next, let's implement the add function. And what that's going to do is it's going to add a tuple to our sliding window, which means it's going to go on one of our heaps. First, we're going to turn this value and index into a tuple, and then we're either going to add the tuple to the max heap, or we're going to add the tuple to min heap. So what are our conditions for adding to max heap? Well, if both heaps are empty, then according to our rules, if the total number of elements is odd, then that one extra element goes inside the max heap, right? So if we want to add a 1, then the 1 should go into the max heap. If max heap is empty and min heap is empty. Are there any other cases? So let's say, for example, our heaps look like this, 1, 2, 3, 4, and we want to add a 1. What we can do is we can look at the top element of max heap and say 1 is less than or equal to 2, so this 1 would go here. So, or value, which is this 1 here, is less than or equal to max heap dot first, so this top element here, dot value, then max heap dot add tuple. And those are the two cases where we would add to max heap. So all other cases we would add to min heap. What if this were to happen? We have the elements 1, 1, 2, 3, 4. So our heaps are balanced right now, but we want to add a 1. Now, according to our rules here, we would add to the max heap, but then our heap is now unbalanced. So what can we do to fix this? Well, we already wrote a function to balance our heaps. So just in case our heaps become unbalanced, let's call balance heaps. Next, let's implement the remove function. And what this function does is it's going to remove a value from our sliding window, which means it's going to remove a value from one of our heaps. First, let's convert value and index to a tuple. And what we simply do is we say if max heap contains the tuple, then remove the tuple from max heap. Or if min heap contains the tuple, then remove the tuple from min heap. And just like previously, our heaps might become unbalanced, so we should call balance heaps just in case. Now we can finally move on to our main algorithm. So first we need to initialize our output, which is going to be an array of doubles. And the size of this is nums.length minus k plus 1. And I'll show you how I get that with an example here. Suppose our input nums is the array 1, 2, 3, 4, and k equals 1. So our sliding window is of size 1. And the size of our output is asking how many sliding windows can we make? Well, we can make 1, 2, 3, 4. So that is nums.length, which is 4, minus 1, which is k, plus 1, which equals 4. So that's how we get this here. Next, we need to initialize our sliding window. Let's say that our sliding window is now of size 3 instead of 1. How would we initialize this? To do this, we say for int I equals 0, I is less than k, I plus plus, add nums I. So our window by the end of this should look like So we're going to start from I equals 0 to I equals 2, which means the end of our window should look, by the end of this for loop, our window should look like this. Next, we are going to move our sliding window until we reach the end of the input nums. First, we're going to start off with two variables, left and right. Those are going to be here and right here. And then we say while k is less than num's length, or in other words, while we haven't reached the end of the input nums, we are going to first get the median of our sliding window and add it to the output. Right now, our output should have nums.length is 4 minus k, which is 3, plus 1, which is 2. So our output should have 2 elements. So we get the median of our current window, which is 2, and we add it to the output left, which is at 0. So 2 here. And then we need to move our sliding window over by 1. So we need to move it here, which means first we remove this left element here. Remove nums left, which is at index left. And then we need to increment the left pointer to move to here, left plus plus. Or we can just combine those two lines of code. And then we need to add right. So right now our right pointer is pointing at 4. So what we need to do is add nums right and right plus plus. So now our right pointer is pointing here at the end of the array, and our window is now 2, 3, 4. And k is actually at, oh, sorry, this should be right. While right, so right is already reached the end of the array, which means we break out of this loop. But if you notice here, our output is still missing one value. So what we need to do is add the same line of code here. Add the median of our sliding window to the output. And so left is currently at position 1. And so we just add the median here. And then all we need to do is return the output. Next, let's run this code and see how we do. Okay, great. The time complexity for this solution is O of n log k. And the space complexity is O of k, which is the size of our sliding window. That's going to be it for this video. Thank you for watching. Please like, comment, and subscribe.